Hello, and thank you for joining me. At this point, we are midway through the videos, so let's recap what we have gone over. Video 1 discussed setting up a simulation class that is responsible for running the simulation. In Video 2, we saw how we can define our species object, and in the last 3 videos, we learned how we can specify the genotype-phenotype map. In particular, in videos 4 and 5, we learned about functors that are useful tricks that we can use in other parts of the code. In this, our 6th video, I will introduce you to how you can use SPEGG to simulate reproduction, which involves operations like choosing the parents. When we simulate reproduction and breeding, we will need to keep track of who the parents are. Now, there are often functions that we are only interested in evaluating among parents. For example, it won't make sense for us to track the fecundity of those individuals that are not reproducing in a given time step. So what we will do is create a demo species parents class that will be in charge of keeping track of who the parents are and storing the functionality that we will use to manipulate our list of parents. So let's create a header file, which we'll call demospeciesparents.h. I want to point out that SPEGG actually includes code for a base class of parents that does most of the common operations, such as summing up the number of reproductively viable males and females in a population. So in our demo species parents header file, we'll actually create a class demo species parents that will inherit from this parent class. We'll define our headers as usual and import the base parents class header file. Eventually, this parents class will be used by our demo species object. Recall from video 2 that we had an include demospeciesparents.h command in our demo species header file. However, the demo species parent object will require using this demo species object as an input. We can't ask the header file for demo species parents object to include the demo species object header file, as this would create circular dependency among our header files. So instead, what we will do is use what is called a forward declaration. By using a forward declaration of the demo species class here, we can sidestep the problem of circular dependency among header files. Now the functions that act as an interface to the parents class are already defined in the base parents class. So the only public function we will need here is the constructor, which is going to depend on the demo species class, which we just briefly defined in our forward declaration. The demo species object will serve as the input for our parents class. The remaining variables and functions are not needed by our demo species object, so we will keep these protected. This is where variables that govern properties such as the age and size at maturation can go. But to keep things simple, we'll only track one phenotype, the fecundity phenotype, as described in our previous demos. So we will create an integer variable that tracks this phenotype's index called fecundity phenotype index. Now if you look briefly at the parents class header file, you'll notice that there are several virtual void functions that are classified as protected. Most of these have default implementations in the parents class that we won't need to change. But in our simulation, there are 2 functions that we will need to modify to apply only to our demo species parents class. The functions determine probability individual becomes female parent and determine probability individual becomes male parent. What these functions do is take information on the fecundity and reproductive state of individuals and then determine how likely any given individual is to contribute to the next generation. We'll see how this works in detail in just a bit. Now that we've defined the parents class for demo species, let's specify how this functionality works. So we'll create a corresponding demo species parents.cu file to our header file that will implement the definitions from our header file. We'll need to import our header file that contains the class definition, and at this point we can also import the header file for the demo species object. Note that we no longer are working with header files, so we don't need to worry about circular dependency here. The first thing we want to do is make a constructor. Our constructor will inherit from the constructor of the parents class, and in this example, we're only working with a single variable that's unique to the demo species class. Thus, the constructor need only contain a line that specifies the value of the fecundity phenotype we defined before. The only thing we now have to do is to spell out our two functions, determine probability individual becomes female parent, and determine probability individual becomes male parent. Let's start with the function that is responsible for determining the probability that an individual becomes a female parent. For our very simple model, we'll just assume that all female individuals will reproduce. Now in the base parents class, there is a vector called will reproduce f that is responsible for tracking whether individual females will reproduce. This determination occurs before the function determine probability individual becomes female parent is called. What we will do is therefore multiply an individual's fecundity phenotype by this vector, will reproduce f, that contains indicator variables, that is, a series of zeros and ones that specifies whether or not that individual will reproduce. In other words, the ith element of will reproduce f is equal to 0 if the individual is not a reproductive female, and is equal to 1 if that individual is a reproductive female. To perform our multiplication in parallel on the GPU, we will use a function from thrust called multiplies and transform that will carry out the operation on a large number of individuals simultaneously. What we first do is define an operation which we'll call OP, which will multiply two floating point numbers together and return a floating point variable. In thrust, we can declare this function as thrust multiplies OP. Now what we want to do is multiply our vector of indicator values, will reproduce f, by the fecundity of individuals and store the results in probability individual becomes female parent. Thus, non-reproductive females as well as males, whose will reproduce f values are 0, will also have a 0 probability of becoming female parents, and individuals with higher fecundity values will have a higher probability of becoming female parents, as we would expect. To perform the multiplication operation in parallel, we call a function thrust transform, and we will specify 5 arguments. First, a pointer to the beginning element of the vector we want to use in our multiplication, and next, a pointer to the ending element of this same vector. Our third argument will be a pointer to the second vector we want to use in our multiplication, in this case, the phenotype vector storing individual fecundity values. And our fourth argument will point to the first element of the vector in which we'll store their product, that is, probability individual becomes female parent.begin. Finally, we'll specify the OP operation we defined above, which consists of floating point multiplication to this function. And in exactly an analogous manner, we'll define the probability that an individual becomes a male parent using the will reproduce m vector instead of will reproduce f. As noted above, your customized parents class can be more involved. For instance, rules governing the size at maturity of individuals and the nonlinear reproductive skew in the species you're simulating could be incorporated. In the next demonstration, we'll go over how we can use this parents class to actually simulate reproduction inside our demo species class. Thank you again for watching, and if you have any questions, shoot me an email via our mailing list, speg-users@googlegroups.com.